Nuclear power plant flanked by cooling towers. A nuclear reactor is contained inside a spherical containment building. A nuclear power plant, sometimes abbreviated as NPP1, is a thermal power station in which the heat source is a nuclear reactor. As is typical of thermal power stations, heat is used to generate steam that drives a steam turbine connected to a generator that produces electricity. As of 2018, the International Atomic Energy Agency reported there were 450 nuclear power reactors in operation in 30 countries around the world. 23 nuclear plants are usually considered to be base load stations since fuel is a small part of the cost of production, and because they cannot be easily or quickly dispatched. Their operations, maintenance, and fuel costs are at the low end of the spectrum, making them suitable as base load power suppliers. However, the cost of proper long-term radioactive waste storage is uncertain. Systems. The conversion to electrical energy takes place indirectly, as in conventional thermal power stations. The fission in a nuclear reactor heats the reactor coolant. The coolant may be water or gas, or even liquid metal, depending on the type of reactor. The reactor coolant then goes to a steam generator and heats water to produce steam. The pressurized steam is then usually fed to a multi-stage steam turbine. After the steam turbine has expanded and partially condensed the steam, the remaining vapor is condensed in a condenser. The condenser is a heat exchanger which is connected to a secondary side such as a river or a cooling tower. The water is then pumped back into the steam generator, and the cycle begins again. The water-steam cycle corresponds to the Rankine cycle. The nuclear reactor is the heart of the station. In its central part, the reactor's core produces heat due to nuclear fission. With this heat, a coolant is heated as it is pumped through the reactor, and thereby removes the energy from the reactor. The heat from nuclear fission is used to raise steam, which runs through turbines, which in turn power the electrical generators. Nuclear reactors usually rely on uranium to fuel the chain reaction. Uranium is a very heavy metal that is abundant on Earth, and is found in seawater as well as most rocks. Naturally occurring uranium is found in two different isotopes. Uranium-238, U-238, accounting for 99.3%, and uranium-235, U-235, accounting for about 0.7%. Isotopes are atoms of the same element with a different number of neutrons. Thus, U-238 has 146 neutrons, and U-235 has 143 neutrons. Different isotopes have different behaviors. For instance, U-235 is fissile, which means that it is easily split and gives off a lot of energy, making it ideal for nuclear energy. On the other hand, U-238 does not have that property, despite it being the same element. Different isotopes also have different half-lives. A half-life is the amount of time it takes for half of a sample of a radioactive element to decay. U-238 has a longer half-life than U-235, so it takes longer to decay over time. This also means that U-238 is less radioactive than U-235. Since nuclear fission creates radioactivity, the reactor core is surrounded by a protective shield. This containment absorbs radiation and prevents radioactive material from being released into the environment. In addition, many reactors are equipped with a dome of concrete to protect the reactor against both internal casualties and external impacts. 10. Pressurized water reactor. The purpose of the steam turbine is to convert the heat contained in steam into mechanical energy. The engine house with the steam turbine is usually structurally separated from the main reactor building. It is aligned so as to prevent debris from the destruction of a turbine in operation from flying towards the reactor. Citation needed. In the case of a pressurized water reactor, the steam turbine is separated from the nuclear system. To detect a leak in the steam generator and thus the passage of radioactive water at an early stage, an activity meter is mounted to track the outlet steam of the steam generator. In contrast, boiling water reactors pass radioactive water through the steam turbine, so the turbine is kept as part of the radiologically controlled area of the nuclear power station. The electric generator converts mechanical power supplied by the turbine into electrical power. Low-pole AC synchronous generators of high rated power are used. A cooling system removes heat from the reactor core and transports it to another area of the station, where the thermal energy can be harnessed to produce electricity or to do other useful work. Typically, the hot coolant is used as a heat source for a boiler, and the pressurized steam from that drives one or more steam turbine-driven electrical generators. 11. In the event of an emergency, safety valves can be used to prevent pipes from bursting or the reactor from exploding. The valves are designed so that they can derive all of the supplied flow rates with little increase in pressure. In the case of the BWR, the steam is directed into the suppression chamber and condenses there. The chambers on a heat exchanger are connected to the intermediate cooling circuit. The main condenser is a large cross-flow shell and tube heat exchanger that takes wet vapor, a mixture of liquid water and steam at saturation conditions, from the turbine generator exhaust, and condenses it back into subcooled liquid water, so it can be pumped back to the reactor by the condensate and feed water pumps. 12 Full citation needed. Some operational nuclear reactors release non-radioactive water vapor in the main condenser. The wet vapor turbine exhaust come into contact with thousands of tubes that have much colder water flowing through them on the other side. The cooling water typically come from a natural body of water such as a river or lake. Palo Verde Nuclear Generating Station, located in the desert about 60 miles west of Phoenix, Arizona, is the only nuclear facility that does not use a natural body of water for cooling. Instead, it uses treated sewage from the greater Phoenix metropolitan area. The water coming from the cooling body of water is either pumped back to the water source at a warmer temperature or returns to a cooling tower, where it either cools for more uses or evaporates into water vapor that rises out the top of the tower. 13 The water level in the steam generator and the nuclear reactor is controlled using the feedwater system. The feedwater pump has the task of taking the water from the condensate system, increasing the pressure, and forcing it into either the steam generators, in the case of a pressurized water reactor, or directly into the reactor. For boiling water reactors, continuous power supply to the reactor is critical to ensure safe operation. Most nuclear stations require at least two distinct sources of off-site power for redundancy. These are usually provided by multiple transformers that are sufficiently separated and can receive power from multiple transmission lines. In addition, in some nuclear stations, the turbine generator can power the station's loads while the station is online, without requiring external power. This is achieved via station service transformers which tap power from the generator output before they reach the step-up transformer. Safety and accidents. Hypothetical number of global deaths which would have resulted from energy production if the world's energy production was met through a single source. In 2014, Professor of Sociology Charles Perrow states that multiple and unexpected failures are built into society's complex and tightly coupled nuclear reactor systems. Such accidents are unavoidable and cannot be designed around. 19 An interdisciplinary team from MIT has estimated that given the expected growth of nuclear power from 2005 to 2055, at least 4 serious nuclear accidents would be expected in that period. 20 The MIT study does not take into account improvements in safety since 1970. 21-22 The most serious accidents to date have been the 1979 Three Mile Island accident, the 1986 Chernobyl disaster, and the 2011 Fukushima Daiichi nuclear disaster, corresponding to the beginning of the operation of Generation 2 reactors. Modern nuclear reactor designs have had numerous safety improvements since the first-generation nuclear reactors. A nuclear power plant cannot explode like a nuclear weapon because the fuel for uranium reactors is not enriched enough, and nuclear weapons require precision explosives to force fuel into a small enough volume to go supercritical. Most reactors require continuous temperature control to prevent a core meltdown, which has occurred on a few occasions through accident or natural disaster, releasing radiation and making the surrounding area uninhabitable. Plants must be defended against theft of nuclear material and attack by enemy military planes or missiles.